Alright, so as we mentioned, today we are doing symmetric cryptography, not asymmetric. And the most common symmetric crypto system of block cipher would be the AES block cipher. So for the rest of the afternoon, we'll be basically focused on AES. And as of now, we'll start by going through the most simplest version, which is I.YCEP. So AES represents the advanced encryption standard, which is it itself is basically a standardized form for symmetric crypto systems per NIST. NIST is the US National Institute of Standards and Technology, which is responsible for creating like cryptographic standards. And AES is one of the most commonly used symmetric crypto system, and symmetric because it uses a shared key for both encryption and decryption. Next slide. And one of the more interesting things is that AES is used in a very ubiquitous way. So it's used in a lot of applications, and for example, it has been used in Chrome, for instance. So if you look at Google Chrome, especially if you look up Chromium code search, which is the closest public thing you can find regarding the source code behind Chrome, you see that there's a lot of like usage of things like AES, for instance. Like AES appears like multiple times here, and you see that there's multiple like letters after, like AES 128CTR, AES 128GCM, so on and so forth. We'll go through what those are in a moment. Next. So how AES generally works is that AES encrypts messages into blocks, where every block is 16 bytes long. So if you have like a 48-byte message, it will encrypt it in 3 different like 16-byte blocks each, because 48 is like 16 times 3. And usually the message blocks are always in sizes multiples of 16, and the key is also in the size as multiples of 16, and the subtext block is also sizes of 16 as well. Next slide. So if you want to look at AES internals, which if you take the diffusion and confusion, you may find certain things are similar. So let's open up to the floor. Anything about this that looks familiar to you guys when we look at what I.YCEP is doing for encryption? Yes, shift from each colors at key are very similar to what we've already discussed. Anything that's new that you have not seen here yet?
Subbytes.
Yes, subbytes is new. We will be going through what subbyte does much later if we have time. And that's it. One thing to note is that add round key and add key are actually slightly different. While add key adds the same key over and over again, add round key actually adds a different round key. AES actually takes in the key and it kind of like splits the key into multiple round keys, which it then uses in this encryption algorithm. But we'll cover that later. Next slide. So while I.YCEP is interesting and AES internals is very convoluted and complex, we will first view AES as a black box. So how do we use AES to do encryption and decryption? It's quite simple. So once you've installed PyCryptodome, you can just from crypto.cipher import AES. You define a 16-byte key, a 16-byte plaintext, or let me show that the lengths are multiples of 16. If not, you have to use padding, which we'll go through later. Then you define a cipher, which is like AES.new with the key, and you have to specify a mode. We'll go through what modes are in a bit. Afterwards, you can just use cipher.encrypt and cipher.decrypt to encrypt and decrypt plaintexts and ciphertexts respectively. Keep in mind that the decrypted, when you run this code, it should be the same as plaintext. You all can have up to maybe 2 minutes to kind of try this out and test it out, I suppose. Yeah. give you all like maybe like 1 more minute and then we will continue with the presentation or with the lecture.
Okay, so now I'll be going through a short demo of AES. So let's just copy the code first. And I'll do everything in a Python shell. Oh. That's weird. Oh,
Oh my god.
the quotes. Because in Google Slides, it automatically formats the quotes. Okay, so now you can see that this is a key and this is the plain text. And so if we look at the ciphertext and we look at the decrypted ciphertext, you notice that the decrypted ciphertext is the same as the plain text, which is exactly what we want, as you can see over here. And also, I'll now be demonstrating diffusion and confusion. So let's say we change a 1 byte of the key. So let's say, not the key, sorry, the plain text. So let's say the plain text is 16 byte plain text. Let's change the T to a capital T. So this is the plain text, and we can call it encryption on it. So, and let's look at the original ciphertext. We can see that the original ciphertext is it's very different from the new ciphertext. And the same goes if we change the key. So let's just do key equals to key colon -1 plus a capital Y. So if we do cipher.encrypt plain text, we'll see that, wait a minute, oh, I didn't redefine the cipher, oops. Here, so you can see that the ciphertext is also extremely different between the two occurrences. So this one and this one. Okay, so now we'll be moving on.
Yep. Next slide. So as mentioned before, you may notice that when you're implementing AES, when you're implementing AES as a black box, you can specify the mode equals to AES or mode ECB, for example. And this is because AES has different modes of operation. So mode ECB is the standard or the default mode that we've been building to. Mode CTR is counter mode, CBC is known as cipher block chaining, and one of the more common ones that you will see today is mode GCM, which is Galois counter mode. We won't be covering GCM for this workshop, but we will be exploring CTR and CBC later on. Next slide. And for as of the different modes, they essentially use AES mode ECB, but they use it differently in how they encrypt stuff. So for example, counter mode uses ECB as a stream cipher, and CBC mode uses ECB as a more secure alternative. Sorry, against ECB Penguin. We'll be learning about these two later on. Next slide. And now that we are familiar-ish with how AES is used, we are going to do a practice challenge called fletchling.py. The gist is I wrote a new custom AES mode, and you have to find a way to break it essentially. This is the one where you will have to interact with a NCAT server. Are you demoing from those? Yeah.
Okay, so let's take a look at challenge. I'll be going through a new Python library called Pwn tools, and you might be thinking, why are we doing this if we're not learning Pwn, right? It's because in this challenge, let's just take a look first. You'll see that you need to input 256 different interactions into the remote, and that can be really tiring. So instead, we use Pwn tools to automate it, and the netcat's not loading. Okay, it just loaded.
So for reference for this challenge, you'll be interacting with the server at trials.I.YCEP.blahaj.sg. The port number is 52000. You can actually see this in the CTFD, I believe, in the challenge name/description. I think it should be up there. Yeah. So you will be interacting with this server instance, which will contain the flag, and you essentially have to, by interacting with the server, find a way to either leak or derive the flag.
Yeah. So we can first import the remote function from Pwn tools, because everything else. Okay, there's one other it's not function, sorry, it's an object that is relevant would be process, because you can do something like process equals to Python 3 IO equals to process Python 3 child.py or whatever for local testing, but we can just skip that for now for this demo. We will proceed straight to the interacting with the remote, which is IO equals to remote, and then it shows the server IP as well as the port. Here IO stands for input and output, and after that you can receive a line. So I'm going to demo netcatting to the remote. You can see that there is a useless line here that says hello, so we just receive it and just get it over away. And after that we have flag equals to this, which will be printed out to us. And after that we'll receive until this prompt, and we can send whatever we want, and then we can take a look at the output. So if we were to go to fledging, you can see that firstly we will get the encrypted flag, and after that we will get the next prompt, or should I say the next output prompt, which is your ciphertext, but this should also be stripped away, so we can just ignore it. Let's receive once to get rid of it, and now we can get our own ciphertext that we need, and from here we can just pass it like we would with any other data in Python, and we can solve the challenge. So we'll give you about 20 minutes to solve this challenge. It's slightly harder than the previous challenges, so we'll give you all a bit more time. All the best.
Okay, so I will be doing a demonstration of the solution for 3C fledging. So we first start by looking at the script here. So you will notice that, okay, wait, let me move this out a little bit more. So we see that this code is interesting. So you have this custom mode called AES mode fletchling. It takes the plain text and the key, and it returns a list of items. We see that it initializes an ECB cipher. And for I in plain text, so for every byte in the plain text, it's going to convert that one byte specifically to a byte of size 1, and it's going to add /x0f 15 times to the message. This message block is then going to be of length 16, because this is 1 byte followed by 15 bytes, so it's 16 bytes and it's encrypted. The ciphertext block is then the hexadecimal representation of that, and the ciphertext is going to be a list of each of these ciphertext blocks. And we realize that each block is actually the encryption output of one character with 0f padding. So now we look at the main code. So we have the flag that we don't have access to, a random key that the server generates every time, and we see that it sends us the encrypted flag. Then we can send the plain text to it, and then it encrypts it for us and sends it to us. So that seems pretty simple. And you will notice that the main vulnerability is that each message block is actually only influenced by 1 byte in the plain text. Every plain text byte will only represent one ctext in hexadecimal that is affected. What do I mean by that? So if I were to NCAT the relevant server, you see that encryption flag is going to be a bunch of like hexadecimal strings. So it's a list of 1 string, 2 string, 3 string, dot, 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 dot. And you notice that, let's say if I enter like A, B, C, D, if my understanding was correct, if my theory is correct that it's only encrypting every byte one at a time, then the ciphertext will be a list of 4 items. Each item will correspond to A, B, C, and D. So if I enter, you see that there's exactly 4 items in the output: A, B, C, and D, or like one corresponding to A, corresponding to B, corresponding to C, corresponding to D. And to double check, if I send like A 3 times, you'll notice that the ciphertext is the same. Each of these values is the same, and even so, this A corresponds to this A. So it's quite clear that every A is going to encrypt to the same output because it's ECB. At the same time, if every byte is being used for one transmission, notice that the first byte is 56F4 followed by EF75, right? Look at what happens if I type IY. 56F4 and then 6938. Wait, what? Oh yes, so notice it's like 56F4 followed by 6938. If I type I and Y, I see that I actually get the same exact values as well. So if I do like I.YCEP open braces, you'll notice that these values, you see EF and 6A. If you scroll back up to the encrypted flag, you see that EF and 6A are also here. So this is the main reason, the main vulnerability in AS mode fletching is that every byte is being used for one message block. Which means that in theory, if I get A, B, C, D, E, F, dot, 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 if I input all of these in one go and I store every of this value, we can match this to the encryption flag and see which one it is to figure out the exact answer. The thing is, this is going to be a lot of coding. This is a lot of like manual reading. So we are going to write a solution code that uses pwn tools to iterate the server. So we're going to do from pwn import remote, and then we'll do r equals to remote I.YCEP.blahaj.sg with port name 52000. Then we are going to do so first off, we know that it's going to send the following words. You're going to send hello, exclamation mark, new line, and then encryption flag. So we're going to use receive until, which will read until it receives this particular sequence, which will be hello, new line, and then and enc underscore flag equals. So this will receive everything up until this point. Then we are going to read the encryption flag. Because when we interact with the server, it's going to print encryption flag equals followed by the actual item, which is a list. We're going to read the entire line. So we're going to do r.receiveLine.rstrip. And here's the thing, if we print this, we'll see that it actually prints out the exact list of the encryption flag list of items. You'll notice that the I here and the Y here are different values. That's because the key is random every single time. So we will always get different encrypted outputs. But we see that it's actually being read as a byte string. So we want it as a list, but we want it as a list. Therefore, we're going to do here, instead of r.receiveLine.rstrip, we're going to say a encryption flag, which is going to be a list object, equals to eval r.receiveLine.rstrip, and then we'll add a, I believe we can add a .decode as well. .rstrip is there to remove the new line character, and .decode is to convert it to a string that we can then run eval. Eval will receive a like the open square brackets followed by the rest of the items. So now if we do print encryption flag and something like say print encryption flag 0, like let's say we're trying to interact it with as if it was a list, and we were to run this code, you'll see that we are able to interact. We have now received it as a list object, and we want to interact. Let's say the first item, you see that we can get this, and then if we do print list 0, we get this value. So this is how we can use pwn tools to essentially read items from a server and to parse it meaningfully. So now that we have encryption flag and we can use it like a list, we're going to start sending our dictionary of items. So we are going to do for I in range, let's say we can do 256 because we can use it that many times. We're going to do r.receiveUntil. Well, we don't have to put enter plain text, new line, and then arrow arrow. We can just skip all the way to the first arrow arrow, which when it expects us to send something. And then we're gonna say a payload could be we just do long 2 bytes of I. Actually, we instead of doing from I in range 256, we can just do from I in range 32 to 128. where this is in essence 32 to 128 is basically running through all the list of printable characters that we have per the ASCII table. So we're going to convert this to bytes 1, and then we're just going to send this payload directly. So r.sendLine payload. Sendline requires you to send a payload as in bytes, and we're just going to do from crypto.util.number import long 2 bytes. For those of you wondering what the 1 in long 2 bytes is doing, so when I do long 2 bytes of an integer, I can use this number to set how many bytes it will take. So we send this as a payload, then we do r.receive until your ciphertext, and then we will be able to read the ciphertext. Again, it's going to be written as a list, so we're going to say our encryption data equals to eval r.receiveLine.rstrip.decode, and then we're going to add the new line here because it's going to print your ciphertext with a new line in here. Then it prints what we want. So just to make sure that this is working as intended, I'm going to say print I followed by encryption data 0, because encryption data should be a list. And I'll just pause for a few moments while you guys look at this, and I'm going to go and test this on the server, and you'll see that for every I value we are able to read the exact 32 hexadecimal output of the encrypted value. And for every flag for every value in encryption flag, it must correspond to one of these. So I'm now going to do something else. I'm going to do a dictionary. So are you guys familiar with Python dictionaries? Alright, let's see some notes. So the idea is that if I have a map, which is like a dictionary, I can do something like in here I can do map. So map encrypt data 0. This is going to map every like actual encrypted output, which is the 32 byte long data, and let's just do map this equals to I. Now, once I've done that, I'm going to now map the remaining items in encryption flag, and we'll find the corresponding things in our map over here. So we'll do for item in encryption flag. So every item is going to be like our like hexadecimal value. We're going to find the corresponding item. So map item, it will point to the exact value on like which I we are going for. So we'll do flag equals to a list. Then we do flag dot append map item. So map item. So let's say if the first item is going to be the encryption of the letter I. In our previous code, when we did for I in 32 to 128, we are going to at some point send the payload that contains I, and then we'll receive the data and we'll store it in here, and we'll point it to that specific value. So we'll do flag.append, and then if this works and we do print flag, we should be able to get the flag. So we're going to try this out, and hopefully this works. Yep. So we see that we get a list of numbers. We are going to convert this to bytes. So print bytes flag. And now when we run the script, it's going to run I equals 32, I equals 33, and then it will reinterpret this list of items from 105.121.99.101. It's going to reinterpret it as bytes, which gives us the flag here. Yeah. I'll give you guys maybe around like 5 minutes or so to kind of read the source script. Meantime, if anyone has any questions on how this script works, feel free to raise your hands and ask around. Yeah.
You know that the line character is like so much when you line character in a moment yeah, you realize that. Yeah, but then because my payload to like because the new line makes new line right, then it didn't send the key, and then I wrote down for like few minutes.
So for reference, like what I'm doing. So now what I'm doing is that I'm just modifying my script to basically like print every byte value that I'm testing. I'm send this single character to the server. I record the exact output that the server will send to me, and then if once this is done and I get the list, I manually like from encryption flag kind of like find it in the dictionary and then map it back over to the value. Yeah.
Hi guys, so we're gonna be going through stream ciphers and I.YCEP now after going through block ciphers. So I.YCEP stands for AES counter mode, where it's like a different mode from I.YCEP. So remember earlier we mentioned XOR and we had the function add key, which was many sites back in the morning. So I'm just gonna ask you, let's say we had just an add key as an encryption. Is it secure? Like barring all the diffusion, confusion, whatever, is it secure? Like let's say you only have one encryption. Yunwei, would you like to answer?
Wait, if you only have the ciphertext and you don't have either a message or key, then it's secure.
Yes, that's correct. It is secure, but there's a lot of problems. So one of them would be that if your key is really, really long or really, really short compared to your message, you can leak one of them. Because, okay, so let's just say, like, I'm gonna pull up Python. And let's just say your key is equals to 676767 and your message is 1. Keys or message, it's just gonna be very close to key because XOR only affects like the last bit because 1 is just 1 bit long. Oops. Okay, so with that in mind, in order to ensure that the key is always as long as the message, we're gonna need to do something called a key stream. And what a key stream does is it takes a short key of like some size. So normally for CTR it's something like 16, 24 or 32 bytes, but we'll cover that later. And it outputs a key stream of theoretically infinite length. In reality it's like really long, like a few trillion long, but in theory we assume that it's infinitely long. And so instead of XORing with the key, we XOR with the key stream output, which means that as long as the key stream is not reused, hint hint challenge later, we have a secure encryption. So far, does anyone have any questions? Okay, so if you want some illustrations, you can refer to the whiteboard here. Okay, so moving on, some intuition or more of a diagram of stream cipher is that you input a key and after that the key stream is generated and that is XORed with the message in order to obtain the ciphertext. Now, question, since XOR is commutative, or should I say A XOR B is A, right? Not commutative, sorry. Is encryption the same as decryption? Yes, it is. It's the same. So that is also a problem that we will explore later. But now back to key stream use. So let's say this is your encryption algorithm, which it just XORs with the key stream. If you know one plain text, you know that corresponding key stream if you have the ciphertext. And so you can get the key stream and you can decrypt anything you want, which is not what we want. So instead, okay, wait, sorry, this is the attack. So let's say we know one ciphertext and one plain text. We can get the key stream. And after that, since we have the key stream, which is equivalent to the key in this case, can anyone tell me how we can use the key to decrypt?
Use the key.
Yeah, use the key stream to decrypt. Anyone? How about you? Would you like to answer?
Sorry again.
Yes, that's correct. So recall that an encryption is a XOR and a decryption is the same, so it's also a XOR. Which means that here, we can just recover the key stream and after that we can XOR it with C2 to get P2. And so this is a problem. So does anyone have any idea how we can fix it? With each encryption we have a different key stream. I mean, I haven't covered this yet, so it's okay to like not know about it, yeah. So I'll introduce something called a nonce, which stands for number used once. And what it does is that it provides an element of randomness to the key stream. So here let's just assume that the nonce works in a black box to sort of influence the key stream. I'll explain the internals later. And given the key stream, we can again perform encryption and decryption. And while the key remains constant, the nonce is sent to anyone receiving the ciphertext. So as long as you have the key, you can always decrypt by generating the key stream. And this is very effective in protecting against attacks, because of the way the key stream works. And why the way the key stream works helps it is because the key stream is generated with I.YCEP. And if we recall earlier, I.YCEP has very strong diffusion and very strong confusion. So since the way CTR works is that the nonce is appended to a byte version of the counter, and that is encrypted with ECB with the key. So the counter will increment for every block. So block 0 will be 0, block 1 will be 1, etc. etc. The nonce is the constant. But since we are changing 1 byte of the nonce, the counter, we are changing 1 byte of the plain text that's being encrypted. And that means that the entire key stream will be changed because of good diffusion. And afterwards, like I mentioned before, the plain text will be resolved with the key stream. Okay, so this is just a more equation-based version of the diagram. So the key stream is generated by concatenating the nonce and the key, encrypting it with ECB, and etc. etc. Okay, so over there, Wari is drawing up a diagram of I.YCTR. It's very similar to this one, but it's on the board. Okay, so this is where we start bullying Bob again, and Mallory.
To make sure you understand the diagram.
Okay, sure. Case. You ask?
Do you guys somewhat understand what this diagram is doing, by the way? It's a bit different from the slide diagram. I think the slide diagram does it, explains it better. Alright, so the general idea is that in CTR encryption, you have a nonce, which is like a 12 byte IP, and then typically this nonce is linked to a counter. So the idea is that you're using ECB encryption not to encrypt the plain text, but to derive a key stream with a fixed key. So the reason why we actually use a random nonce every time is because we want the key stream to be unique with every encryption, but we don't want to randomly generate keys every single time. Imagine like you're talking to people and you have to maintain like 1,000 keys. It would be better off if you only have one fixed key. So that's why there's a nonce. The nonce is this randomly generated value that is being used to randomize the result key stream here that is not with the plain text. So the general gist of it is that from in CTR, you start with your nonce, and this nonce is linked to a counter of 0. So let's say your nonce is n. Then I'm going to do ECB to encrypt nonce with my key, and this gives me my first key stream, which I saw with my first 16 bytes into the first 16 bytes of the ciphertext. Then for the next 16 bytes, because you assume that the plain text sizes are always multiples of 16, the next plain text block will be solved with the ECB, encrypted using the same key and the same nonce, but you add a +1 to it. So because of diffusion, when the nonce is increased by 1, this whole output will be very different from this output, which is why that a seemingly new random value is being created and solved with the plain text to get C1. And then this is how like I.YCTR works. So like just so on and so forth. Then to decrypt with the same nonce and the same key, if you have the key, then you can derive this key stream that you can use to solve to get the solve ciphertext to get the plain text. Yeah. Any questions with this? Yes.
Wait, you say that you're keeping a key so that you can keep the person, but if you want to decrypt it, you still have to keep track of the nonce too. So don't you still have to
Yes. So usually the ciphertext is your CP and your nonce. So when you send the data to the user, when you send data to someone to decrypt, you give that person the nonce as well. It's just that the key is unknown, so the person cannot decrypt unless they have the key. Yeah. Does that make sense?
Yeah.
Alright.
Alright, so what he said. Anyway, moving on. So here, we have we're sort of going back to the first few slides where some person called Mallory, which is a malicious person, wants to trick Bob into thinking that Alice hates her. And so, this brings us into a vulnerability of I.YCEP, which is called malleability. And what malleability means is that when someone has knowledge of both plain text and ciphertext, or potentially even less information, they can maliciously modify some ciphertext to decrypt to a plain text that they want. So, like our analogy before, Mallory wants to change the ciphertext to decrypt into "I hate you." So, we recall how I.YCEP works and the encryption equation, which is basically ciphertext equals to plaintext or keystream. And decryption is the exact same thing. So, Mallory wants Bob to decrypt to "I hate you" instead of "I like you." And so she can modify C into C prime and then this equation. As for how this equation works, would anyone like to take a try and derive it or explain how to derive it? It's okay, you can take a guess. How about you?
What does the apostrophe mean?
Okay, so C prime is basically like apostrophe means prime. It basically means like just a separate variable. We just use the prime to denote that it's separate. Yeah. So you could just as well use D, but we use C because ciphertext.
Wait, if Mallory knows message and the ciphertext, right? Then she can get the key stream. So if she can get the key stream, then she can resolve the message she wants with the key stream to get the ciphertext, right?
Yeah, exactly. So over here you will see M prime XOR M. Wait, no, sorry. C, you will see here C XOR M, and C XOR M just so happens to be the key stream. And so we are faking an encryption of M prime by doing keystream XOR M prime. And this will give us a ciphertext that when you XOR it back, because of how XOR works again, you will get M prime. Is everyone clear about this? Make sense? Alright, sure. Moving on. So this is the exact same thing, but it's written out equation by equation. So for those of y'all who are more visual learners, this should help. So again, it's basically faking an encryption by getting the key stream, and after that, after you simplify everything, you will get 0 XOR 0 XOR M prime, which is just M prime. Okay, so we'll give you guys about 15 minutes to do this practice challenge. It involves a stream cipher called RC4. If you have any questions, feel free to sound out. Okay, so now I'm going to be going through RC4. So, can I get everyone's attention? Okay, so let's look at the challenge distribution first. It's quite a short challenge code. And what it does is it just calls RC4 with a key. And RC4 is a stream cipher, so that is something we need to take note of. And also the flag, in this case, is also rejected in a way that makes us think that it's telling us the flag length. So we can check the flag length again. And it's 20 bytes. And let's look at the length of the test message for a good measure. 24 bytes. So we see that the test message is longer than the flag. So this alone is not very useful. But let's look at the below part where we have the ciphertext of both the flag as well as the message. And so, since we have both the ciphertext and the plain text of M1, can anyone tell me how do we get the key stream? Anyone? How about you? Would you like to tell me how to get the key stream? Yes, so you XOR the message as well as the ciphertext. So let's just create a source script. Okay, so first we'll get the output like usual, and we can now introduce you all to the XOR function from Pwn2s, which is very useful because it can immediately take bytes. So what I mean is that, let's say you want to XOR 1 and 2, right? It'll give you 3 obviously. But if you want to XOR x01 and x02, it will give you x03, which is very useful because you don't need to convert to bytes and convert bytes to long and long to bytes. And one quirk that Pwn2s, I wouldn't say a quirk, more of a convenience feature that Pwn2s has, is that if you have one string longer than the other, Pwn2s will repeat the shorter string. So like if it's in this case, it will repeat x01 twice. And let's say it's something like AB and CDEF, right? It will repeat AB twice. So it will become AB, and then it will be XORed with CDEF. Okay, so now moving back to the challenge, we can get the key stream by simply XORing C1 as well as the testing message. Okay, so I'm not going to print the key stream because it's just one line of code, no need to debug. But after that, we can decrypt the flag. So what we need to do is XOR C flag and the key stream, and this will give us the flag. Oh, I didn't print it. Okay, so here we'll get the flag, and we notice that at the back there's a bunch of gibberish. That is because our key stream is 24 bytes while our flag is 20. So the first 4 bytes of the flag ciphertext will get looped back over to the back and then XORed with the key stream, but we can just ignore that because that's gibberish. So we get the flag again, and I'll give you all about 1 minute to copy the code. And once you're done, feel free to attempt 4B Mallory. We'll give you about 10 minutes to do that because that one is a it's a relatively simple challenge when you build off 4E-RC4.
We should show them the.
不要委屈这个
Okay, let's look at the challenge. Okay, so over here we have the flag already, but like, let's just ignore it because it already says here that we're trying to get the program to print the flag. Because if you're a real CTF, the flag would definitely not be here. So what happens is that AES mode CTR is used, where it is used with a key that we don't know and a nonce that we do know. But whether we know it or not, as we'll come to find out, it's not very important. So here Alice wants to tell Bob that she likes him, and Alice encrypts the ciphertext, and we get the ciphertext. So we are Mallory, and we want to torture Bob and tell him that Alice hates him, right? So we can input our own ciphertext to send to Bob, and we need I hate you to be in Bob_ptext, which is Bob's plaintext. But in this case, we can kind of just make Bob's plaintext I hate you exactly without the need for in. So what we can do is we can notice the vulnerability in the challenge, which is that the nonce is reused across both encryptions. So this is similar to RC4, where instead of RC4 having no nonce, here we have the same nonce, which means that the key stream will be the exact same for both ciphers because the same key is used. With this in mind, we can apply AES CTR malleability, and we can forge a fake ciphertext to send to Bob. So what we can do is we can import all the necessary items, the necessary libraries, and we can run the script to just get Alice's ciphertext. So let's just put it as ACT. And wait, oops, I forgot to get the plain text. Wait, no, the plain text is just I like you, right? Yeah, the plain text is I like you, but it's padded. So let's import the padding library. And we can use the magic of Pwn2's XOR to just XOR two values of different data types. Because Pwn2 XOR is goated like that. And this gives us the key stream once again. And after we get the key stream, we can forge a fake ciphertext. So how we do that is we just XOR the message with the key stream. So the target message is I hate you, and it's padded because there's an unpad call. So let's do. Wait, oops. Oops. Okay, so apparently you cannot XOR an integer with a byte string. I thought you could. So we have to convert to bytes with long to bytes. Okay, I seem to not have converted it to a byte string. Okay, so now we will get the target ciphertext, but we notice that if we go into the distribution and we check the challenge distribution once again, we will see that the the ciphertext is taken in an integer. So we have to use bytes to long to convert it back. Okay, so this is a really messy soft script, but in CTFs you generally tend to write code as fast as you can because of time constraints. So this is like your average CTF soft script. And from here, paste it in. Hey, that's weird. Let's see what's the issue. Yes, but this was written with the current value, so that's not the issue.
That was the issue.
That was the issue?
Yeah, because you reread manually at some point, we forgot to.
Oh shit, I did not see that. Wait, good spot. Yep, we got a flag. Okay, good spot. Okay, so now we'll be moving on to block ciphers of the padding section of block ciphers, which is the second last section of today. So we recall that I.YCEP encrypts blocks of sizes 16 bytes. So would anyone like to guess what happens if the blocks are, like for example, the message is 17 bytes?
The last one gets
17 bytes.
The last one will split to another one.
Yeah, the last
It will be split into another one, but what happened after that?
So the subnet mask will be 255.
So you see, right, there's a workshop that's called Web where you can explain this. They will explain this, not me. But okay, this is
first, like the 16 will be like the network.
God.
just gets padded out. The one
Then the
where
last one will be like the host.
Okay, so the answer is, let's just open Python and see. I'll put the key as A for placeholder purposes. Yeah, we get an error. It's not possible because the last block is 1 byte. So yeah, this is just the AES source code that's split into blocks. And this is the specific line that errors. Wait, why can't I? Oh. So the solution to this is something called padding. And the specific protocol of padding we use is called PKCS number 7. What it means doesn't matter, but it is a standard protocol that is very widely used. So like PyCryptodome uses it, and most AES implementations also use it. So how it works is that, let's use an example to illustrate. So say we have 1, 2, 3, 4, 5, 6, and we want to pad it to a string of 10 bytes. So obviously 10 minus 6 is 4, and we need 4 more bytes. So how PKCS number 7 will denote this is it will use 4 bytes of x04, and we remember that x04 is the byte equivalent of the number 4. So this extends to even larger numbers. So for example, if it was just a 1 and you want it to be 10 bytes, then it would be bx01. However, in AES, we normally use 16 bytes because AES block size is 16. And pad always adds padding. Remember that. So we're gonna play a game now. There'll be 3 questions, and the 3 people who answer will get food. So guess the padding results. The first one is this. So this is valid Python code. You can run it, but don't do that because that defeats the purpose of the question. So would anyone like to try?
We can like go through the entire process again.
Oh, yeah.
You want me to go back? Okay, sure.
Yeah.
So it start. So let's say you need 4 more bytes, then you will add 4 times x04 at the back. Yeah, that's how padding works. Yeah, do you have like any questions?
But if like that one got more bytes than that one, how?
Like, so let's say it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1. So it's 11 bytes. Is that what I'm asking?
Oh, okay.
Is that what you're asking?
Yeah.
So then you will pad 9 times because it is to be a multiple of 10. Yeah. Okay, so yeah. Would anyone like to try? Yeah.
You add 6 more 04s at the back, 0x4s at the back.
Are you sure 0x4?
Shouldn't it be X6?
Yeah.
X6. Do we have 1 extra?
Huh?
Do we have 1 extra?
No, we don't.
Oh.
I gave you one because of your.
Okay, sorry, okay, we'll give it to him even though it's a half answer.
The answer is like 6 such as 06. So the padded byte, the number of bytes to pad is the byte that gets added. Yeah.
Okay, so yeah, this is the answer. And next question. This, oh yeah, hello is 20 bytes.
X04.
No,
Wait. 20 bytes.
20 bytes.
Oh, never mind.
The reverse of the
We like to answer.
You guys
X.
padded with slash x0c.
Are you sure?
16. Hello world is 20 bytes, right?
Yep.
It pads to 32 bytes, and 12 is 0xe. Right? So we should pad with 0x. We should pad with slash x0c.
Okay, I'm not sure about this, but there is some. It may not be exactly x0c. I'll explain why. Okay, the answer is x0c, but it may not be exactly x0c. Okay, it is that might then. Because let's say if it was 26 bytes, x0a is new line, so it will be slash n.
Oh.
Yeah, and then slash T I think is 09. Yeah, but that is correct, so I'll give it to you.
Yeah.
So this one is the hardest one. What happens if it's exactly 16 bytes?
Adds 0, 0.
Are you sure?
Doesn't add anything.
No, it always adds.
Add something always.
0, 0.
No, she raised her hand, right?
Wait,
Let me check what is the hex.
what's the hex?
0.
16 is 0, 0 is 1 0.
0x10.
Yeah.
Then that 16 times.
Yeah, that's correct. Okay, so let's just show this because this is a very special behavior. So over here, this 16 bytes exactly. It will add x10, x10, x10. Catch that you.
Can I in the
No.
Okay, so again, this is the answer.
Any questions as to why you don't think there's like 16, there's always like padding that's added?
Yeah, that's the reason. You can take a guess. We'll go through it on the next slide. So I just touched the next slide. You might be able to get something from that. Anyone? We haven't gone through that, so like it's fine to just take a wild guess. Okay, wait. So basically, it's because of something called unpadding, and it has to check the last byte. So like for example, with our first example, which is 6 bytes, and it pads 4 times, it checks that if it's x0 or it's slash x04, and if it checks that it is, and it will remove 4 of the last bytes. And so this is why we need to pad 16 times, even though there's exactly 16 bytes. Because if it checks the last byte to be a letter O, it's just going to error. And also, if let's say the padding string is corrupted, so let's say it's x04, x04, x03, x04, it will error also. Hint hint, this may be used as a primitive. Okay, so now let's just give a short demo. I'll give a demo of unpadding, because I already demoed padding. So let's say unpad this string, right? Because it's padded already. And we have to specify that it's to 16 bytes. Oh my god. Here we get the original message, which is 16 A's. And this goes the same way for, let's say, this is our original example, which is here. So does anyone have any questions so far regarding padding? Alright, if not, I'll move on.
What if I unpad A 256 times?
You mean like yesterday's question?
Like if there's a string of A's, there's at least 256 A's, and I unpad it.
Oh, you mean pad?
No, unpad with respect to 256.
Why you just error cause the pad is valid?
No, A is less than 256.
But yeah, but you meant pad or unpad?
Unpad.
Unpad. Wait, if it's less than 256, you'll just error.
No, it will just delete A's.
Wait, how long is the string?
Like 256.
Okay, wait. Wait, what do you mean? Like, like that?
Is it 256 or is it less?
That's weird. Why is it not erroring?
No, 8 to 9.
That's weird.
Because
I have no clue why this works.
What's RDA?
this is one. What's it?
Oh, okay, yeah.
This is why even when the thing is exactly like evenly paired, you still add padding at the end, because if not, then you're gonna lose data, or you could lose out on the original data.
Is this even exactly 16 bytes? Oh, I didn't. Yeah, the padding is incorrect. Okay, so now moving on to an attack, or should I say a primitive first. It's called I.YCEP Oracle, and these slides were these slides were funny enough made by me for another training, but Wari just decided to plagiarize it.
It's the one sharing, so it's not
Yeah.
plagiarism.
Yep. Oh, this is from yesterday.
Yes.
Okay, so as I found out yesterday, the wood bar is rather poorly located, but we'll just do without it. So ignore this block because it's on wood. But so over here, we remember that every block in AES, ECB, control, is encrypted independently, which means that every block will be encrypted into its respective 16 bytes. Following so far? Okay, let me see. So now, let's imagine we have an oracle that allows you to append some hidden message to the end of your prefix, so you can specify a prefix. That's all you can do, right? That is enough to get you the message. So we're going to teach you how to exploit it. Okay, so first, let's think about how we can reduce the search space of a character to be as small as possible. So one character is 256 bits, 256 possible values because it's 1 byte. So let's force the 1 byte into the last block. How do we do this? Let's say our message is 16 plus 16 plus 16 plus 12 bytes, right? And if we want the message to be one more than a multiple of 16, how many do we need at the start? Wait, never mind. Okay. You need to add 5 because 16 plus 16 plus 12 plus 5 is equals to 17 plus 16 plus 16 equals to 1 plus 3 times 16. Primary 1 math, by the way. And because of that, this shaded area is just 1 byte. And it's the last character of, in this case, the flag. So we know that the last character of the flag is always a close brace. This is not very useful, but we can use it when we are debugging our source script. So, next slide. The question is, how do we check this? Is anyone able to maybe tell me how, like give at least one step on how you can brute force this? Right? It may or may not involve something to do with trying to check if it encrypts or something. Hint. What if we add 16 bytes here? Wait, would you like to answer?
Okay. So because at the end, like at the last block, it's 15 bytes of padding and 1 single byte, right? So at the start, you can make your own single byte plus like 15 bytes of padding. So and then you just like cycle through like all 256 possible bytes, and then you check whether like your first block matches your last block, and if it matches, then that'll be your correct character.
Yep, excellent. So what he's saying is that 15 bytes of padding, we know that this uses PKCS number 7, which means that bytes of padding is just, we know this is the padding, which means that we know every byte except this. So because ECB encrypts 1 block by 1 block, we can check if this block corresponds to our brute force string by inputting our brute force string here. So can you go to the next slide? Yeah, so here's our brute force that is unfortunately on top of the wood. Next slide. So we check if these two are matching, and if it's so, we know that we have gotten the last part of the flag. But now, can anyone tell me how we can generalize this to get the next byte of the flag? Anyone? You change the length of the padding, that's a hint. Alright, okay, it's fine. So, what we do is we add 1 byte to the prefix. By doing this, we force the next byte into the last block. And when we do that, we realize that we again know 15 out of 16 bytes of the last block. So the padding here is not x0f x0f, it's x0 e because in hexadecimal 14 is e and it's 14 times. And from there we just do the same brute force and we just repeat until we get the flag. So I'll give you guys 20 minutes to do this challenge, I.YCEP Oracle. It is by far the hardest challenge so far, so feel free to take your time. Alright, hi guys, so we'll be going through the challenge now. So over here, this is just the exact case of the oracle that we need in order to use the I.YCEP oracle attack. So if we go back to the slides, you'll see that over here there's the prefix, right? And we can inject the prefix over here. So that's the exact scenario needed for us to use this attack, which means that this is just implementing the I.YCEP oracle attack. However, theory and implementation are very different, and this is by no means an easy attack to implement. So let's begin implementing it now. So evidently we're going to need pawn tools because we're going to need to brute force quite a lot. So I'm just going to double check the port. Yep, okay, the port is 52001. So we can initialize the remote. Okay, so we know the flag length is 24, and so we don't need this information because the flag length is constant, so we can just skip past it. Okay, so we just define the flag length as L here first. And now we're going to need to craft our prefix. So I'm gonna do for one character first and then we can iterate through. So evidently, since the flag length is 24, we need the closest multiple of 16 is going to be 32, and we need it to be one more than that, so 33. So we can do a 9-byte prefix. So 9 bytes, and after that, we can add our brute force. So over here it says the characters are only the lowercase letters and underscore and the 2 braces. So we can just type it ourselves. I put underscore at the front because it is the most common character in the flag. Because underscore is used to denote spaces. So we can iterate through the character set. And we can craft our prefix to send, which is gonna be so first we're going to pad our brute force character. So it'll be this, and we can add on our original prefix. So this means that it's gonna be a 25-byte prefix because 16 bytes here, and it'll be extra 9 bytes here. So now we can just send it. I'm going to use a function called sendLineAfter, which has the equivalent of doing so this receive until AAA and send until AAA is the exact same as doing sendLineAfter AAA. So sendLineAfter is in one line, so I'm going to do that. So we're converting the prefix to hex because, as you can see in the challenge, it takes it from hex. And one thing is that we should always send bytes to a remote, so we encode it. We can send strings, but we'll get a nasty error. So I mean not error, a warning. So I don't want to have to get that warning. So now After that, we will receive our ciphertext. So we can first strip away the hex demarcator. And our ciphertext in hex should be our next line. So CT is equals to IO.receive line, and then we convert it back to bytes. And we can check if the CT's first 16 bytes is equivalent to the CT's last 16 bytes, like in the slide. So check these two. And if it if it is, we'll just print the character to know that we have retrieved it, and we'll break. So that's interesting. So let's debug. We can use IO.interactive to get some output. Like as a that's weird. It might be because there's another colon here, and I might be sending after that. That's really weird.
Is it because with the space before the colon?
I think so. Go catch. Yeah, it is. Okay, I hope this works. Yeah, it is. Okay, nice catch. Okay, so we have gotten the last part of the flag, which is the closing brace. So we can define our flag and we can add it on. So we are starting with the last part of the flag, so we don't plus equals, we do flag equals to ch plus flag, because we want the flag to be at the end. Okay, and we can add a print flag for debugging, but right now we are still on the last character only, so we'll just get this, right? So now we need to generalize it. So there are two things we need to change. Firstly, we need to change the prefix length and the brute force string. Let's do for I in range L. So we recall that we need the length of the prefix plus the length of the flag to be 1, 2, 3, 4, etc., etc. Bytes longer than 16 bytes, a multiple of 16. Sorry. So since I starts from 0, we need to add 1 to I to get 1, 2, 3, 4, which means that we need to do some arithmetic manipulation. So okay, let's say j equals I plus 1, where j is the number of bytes that we need to be more than 16. So so the length of the CT, which is the prefix plus the flag, the PT, which is the prefix plus the flag, is equals to k times 16, which is some multiple of 16, plus j. And the flag length is 24, so the prefix length plus 24 is equals to that. And remember, we're trying to get prefix length, so we minus. And we realize that we can get j minus 24 because we know both j and 24. And we want it to be the smallest possible number above k times 16, right? So what we can do is we can work modulo 16, so we can completely eliminate this 16 times k, because when you use a modulo function, it strips away. Okay, how do I say this? A modulo is similar to the remainder that you get when you divide by a number. So for divided by, let's say 5 divided by 2 is 2.5, obviously. So 5 mod 2 is 1, because 5 divided by 2 is 2 remainder 1. So that's basically how modulo works. And this is useful because we want to annihilate this k times 16. So we just do prefix length mod 6, and then we mod 16. Okay, so after that we can just write it out. And we can do prefix equals to some garbage characters times the length. And next we need to change the brute force string, but this one should be doable. Let me find it. Let me find I can't find the line in question. Oops. Okay, here. So we're trying to brute force ch plus. We're trying to brute force the last few characters of the flag plus C that we know plus ch. So let's do this. And this should pad properly. But we also realize that since the flag is 24 bytes, this can go to more than 16 bytes. So we can't just take the last 16. We need to do minus 16, which is the last 16, but we need to go one more if it's more than 16. So in this case, since it's already more, since it can only be up to 32 bytes because the flag is less than 32 bytes, we can just do if length of flag, alright, if I is more than 15 or more than equals to 16 rather. Wait, no. More than equals to 15, because when you pad ch plus flag, which is in this case when I is 15 is 16 bytes, it will become 32. So then we can just write our detection here. And then otherwise we can use the other detection system, which is the one for the last 16 bytes. Oh yeah. Okay, we seem to be getting the flag. Alright, nice, we have gotten a flag. I.YCEP, just keep padding. I'll send the whole script in the Discord because it's kind of long.
You want to send the one you had?
Sorry?
You want to send the one you had B1 much more than you can.
Okay, sure. It's fine, I can send it's fine. Okay, so the script I just posted in the Discord is the one that I used yesterday, which is slightly more elegant. But I'll post both of them. So I'll post the today's one too. Okay, this should be pretty quick because it's just copy pasting. Okay. Okay, now that we've finished ECB Oracle attack, does anyone need any more time to copy or write the soft script?
Do you all want a 5-minute break maybe? If not, we could push through and finish the last few parts that we have left for this workshop. Up to you guys.
This is the last section and 2 more challenges. Alright, I guess we're just gonna go on then. Okay, so now that we finished ECB Oracle, do you all think it can be mitigated? Would anyone like to answer? Yes, it can be. But, I mean, that's obvious because that's why I asked you a question. But, basically, there's this new mode called I.YCEP, which stands for Cipher Blockchain. Blockchain like cryptocurrency. This prevents ECB Oracle attack, and it prevents another attack called ECB Penguin. I wouldn't say it's an attack, I would say it's a property. But if you wish, you can Google ECB Penguin. It basically shows that if you encrypt some data, the relations of the data will still show. So like this ECB Penguin encrypts an image of the Linux mascot Tux, which is a penguin. And you can still see the penguin. So moving on, let's take a look at the CBC diagram. So okay, we'll ignore this again. But so over here, we can see that there are 2 occurrences, or 3 but ignore that, of ECB encryption. So that's why the CBC is built off ECB. But the extension in question is that there exists something called initialization vector, or IV, which will be XORed with the plaintext before it's encrypted. And for the next block, the ciphertext will be brought up to be XORed. So this chain continues. That's why it's called a cipher blockchain, because it chains from one block to another, to another, to another. Any questions so far? Alright, okay, so moving on. Again, we have a demonstration in Python of I.YCEP. So the implementation is largely similar. It's just that instead of saying AES mode ECB, it says AES mode CBC. And the IV parameter is specified over here. Okay, moving on. The ECB, wait, can you go back? Yeah, so ECB Oracle attack is gone, no more. But there are new attacks for CBC, because as with every mode, there are new attacks. This one. Yeah, so there is something similarly to stream ciphers. There is a malleability attack on I.YCEP. So we are going to torture Bob once again and tell him that we hate him. So we are going to go through a more equation-based version of I.YCEP first before we explain the attack. So let's say CT_1, which is the first block, is equals to ECB of M_1 XOR IV. And CT_2 is equals to ECB M_1 XOR M_2 XOR CT_1. And this goes on and on and on. So we can in general we can say that CT underscore I is equals to ECB M underscore I XOR CT underscore I minus 1. Where CT 0 is IV. And so this, other than being very useful for a certain person called Mallory who wants to make board feel sad, is very useful in the real world where we want to gain unauthorized privileges to an admin or like an admin account. So for example, let's say that the data of admin, let's say of whether user is admin, is sent and is encrypted by CBC where the IV is controlled. This on the surface seems quite secure, but it is not because of AES CBC IV malleability. So as an attacker, you of course want to privilege escalate. And so, next slide. The attacker can use this attack in order to gain unauthorized privileges. So I'm going to write it out. Okay, so wait. So since CT1 is equals to, okay, we'll work on a less than 16 byte plain text first because that's simpler. And also the admin case only requires one block of ciphertext because it's really short. It only says admin true. Say CT1 is equals to ECB of PT1 XOR IV, right? Which means that PT1 is equals to the decryption of CT1 and then close bracket and then use all the IV. So let's say we know CT1 and we know PT1, right? Is there a way we can change PT1 to make it something we want? Will anyone like to answer? Alright, it's fine. I'll just go through it. So let's say you want PT1 to be something called like, let's say PT prime. So PT prime will be equals to decrypt CT1, no, CT prime. Sorry? No, CT. Okay. So in some cases we will be given the ability to change CT, but in the challenge that we have for you later, we are not allowed to do that. But it's fine because we can always change IV. So IV prime. So we know this. We want to change this. Can't we just change this? Well, of course we can. So we just submit an IV, a fake IV, which is equals to the decryption of CT I XOR PT prime, right? And this is equals to PT PT1 XOR IV, and then we XOR PT prime. And we're done. We just need to calculate this, and we have gotten a fake CT. Oh, sorry, I did. Yeah, it's here.
IV prime is decryption.
Wait, I think my handwriting is really bad. I'm gonna.
Wait, no, this is correct.
Yeah, my handwriting is just really bad. So. Yeah. Okay. So this is basically what this is going through, and after that we can get a fake plain text. And next slide. So we'll be giving you about 10 minutes to do this. This is much easier than ECB or Oracle. So yeah, we'll be back at 3:50. Okay, hi guys. So we'll be going through CBC IV now. I'm gonna do the entire solve on Python shell because it's short enough. So I'm not gonna write soft script. Okay. Okay, so if we look at the challenge, we basically have a ciphertext of role user. And after that, we need to forge a ciphertext for forge an IV in order for the message to decrypt to role admin, right? And if we go back to the slides, we'll see that we have this equation here, which we derive on the board. And we can just apply this equation. So we also need to notice that before we convert it to bytes, the plain texts are encrypted. So we need to keep that in mind. Not encrypted, they are padded. So we need to keep that in mind. And we also notice that we have the original IV here. So let's just solve the challenge. So we define all our variables. Okay, so here we see the padded message, and then we need to pad the target message. Okay, so we have the target message as well, and after that we can get the Pwn2 XOR. And we have this. So after that, we need to check how to input it, and we see that the IV is inputted in hex, like the prompt tells us to. And we also notice that there's no remote here, and that's because there's only one possible value of IV. So the challenge author, or Worry, has very kindly just allowed us to decrypt the flag with the IV that we have as a key. So this is commonly used in CTF challenges to make a netcat or a remote unnecessary, where you can just validate it locally, because you physically cannot decrypt this without the correct IV. So we can sort of just ignore that and just input the correct IV. So here, and let's get the IV's hex value, which is this. And we just got the flag. Nice. Okay, I'll give you a bit to copy. It's just these few lines. So up to the IV line. Okay, and what?
Yeah.
Okay, so we noticed just now that we had the ciphertext and the plain text that was decrypted, but I have a question. What if we don't have the original plain text? So what if the original message that was encrypted, so it was mode user, right? What if you don't have that? Can we exploit that? Will anyone tell me? Can anyone tell me, if we don't have the plain text, we only have the ciphertext, can we exploit that?
Brute force.
In some way, yes, but I mean the answer is yes. Otherwise, I wouldn't ask you that. But going back to wait, can you go back outside? Okay, going back to I.YCEP, just keep this in mind. Just keep the fact that the three plain text blocks are encrypted independently, and just remember the diagram. So moving on, there is something called I.YCEP padding oracle, where instead of using a CBC vulnerability, we use a vulnerability with the PKCS number 7 padding system, or specifically some implementations of it. So how padding implementations work is that they want to minimize the number of errors, right? Because if you've learned about networks, you may know like stuff like automated repeat requests or checksums, which are meant to prevent corruption of data. And this is no different. It checks if the padding is correct. So let's say you want to decrypt, you want to unpad a message that ends with x04, 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 it'll pass. But if it's x04, x04, x03, x04, it will fail, because that's not supposed to happen. So we can actually use that to decrypt the ciphertext with just this. So this uses both CBC IV malleability as well as the fact that the padding oracle, sorry, not the fact.
The whole idea behind CBC binding oracle is that your C0 or your CI is essentially the ECB of your plain text P0 resolved with the IV. And the whole idea is that during the decryption step, we are just going to do ECB decryption of C0, which is going to return P0 XOR IV. So what happens is that when we control the ciphertext as well as the IV that's being used, it's going to return P0 equals to this thing XOR with the IV. So next slide. Yep. Yes. So yes, show that info. So in a sense, the output is always going to be ECB decryption of C. Okay, if IV is C0 and C0 is C1, it's going to be the decryption of C1 XOR with the previous value, which will usually return the actual plain text. And if this is not properly padded, let's say it doesn't end with, like, let's say 0, 1, or it doesn't end with any number between these, then there will be an error. So we're going to do an investigation where instead of sending in just the regular IV and the ciphertext, we want to send, next slide, we want to send like ciphertext, but we send anything as IV. So like, let's say the IV is X. Then what's going to happen is that when it's decrypting, it's going to reveal ECB decryption of our ciphertext and it's going to XOR it with X. And because we know that this value is our original plaintext before our original plaintext XOR with the IV, the output that this decryption will give us is P0 or P1 XOR with IV, which is our C0, XOR with X. So the idea is that if P1 or C0 or X is properly padded, like for example, if we're looking at the last byte, if we modify our X in our IV such that P1 or 0 or X is slash X01, then it will be like slash X01. This whole thing may be garbled, but it doesn't matter. We see that there's a correct padding. There's exactly one byte of byte 1, so there won't be a padding error in a sense. So this only happens if our P1, which we don't know yet, our C0, which is our original IV that we're given on the previous ciphertext block, XOR with an X that we kind of like brute force is equal to slash X01, then we will know that there's no padding error. The reason why this is important is because if you go all the way back to the setup, the whole setup of CBC padding oracle is when the server decrypts stuff for us where we can send our ciphertext and an IV, but our info is whether or not there's an error that occurs during this process. So this is a scenario where we know if there's a padding error or if there's no error at all. This is the information that we are working with, and you'll be surprised at how often this is actually a thing in real world systems. So we're just looking at whether or not there's a padding error or not, and we're trying to figure out how to derive the plain text given a ciphertext that we don't have the key to decrypt, and we're just working on the existence of this padding error. This is why we are looking at when something gives no padding error, because when we know that there's no padding error, we know exactly what the byte is decrypted to, which we can then XOR back with X to recover P1, P0 or IV. So like if we go from X from 0 to 256, where X is like the last byte in the IV, for example, go to the slides. Yeah, next slide. Next slide. Yeah, so when we find the correct X value, where P1 XOR C0 XOR X ends with slash X01, which is the correct padding. Next slide. Then you'll be able to figure out that the P1's last byte would be slash X01 XOR with X XOR with C0. Or more importantly, we can write this as P1 XOR C0 equals to the last byte slash X01 XOR with X. So that's the whole idea that we're working with here, where because we find the right value whereby there's no padding error by chance, then we will figure out that this has to be the correct padding. So this XOR X must be equal to our P1 XOR with C0. So the whole gist of the attack is that now that once we find this correct X value, we know the ciphertext, we just don't know the plain text. So we use this to actually derive the plain text pretty much that is the gist of the idea. And then let's say we get the last byte of P1. So if we know P1 is like ... with some character like A, for example, then how do we find the next byte? We look at P1, so C0, so a bigger X, like let's just say like just do X2, whereby
now we are looking at very here. We're not looking for an x2 whereby it ends with /x02/x02, because now we're looking for an x whereby the result is a valid padding of size 2. Because when we know this valid padding of size 2, we can figure out that this value, which will do y, we can figure out that y XOR C0 at that index is going to be x2 at that index XOR with the /x02. Then to find an x2 whereby the last byte is going to be 02, because we know what P1's last byte is, we can derive that byte accordingly. I'll demo this with the source script. Yeah. So
Wait, just the original source script.
Sure. Also can. You have it?
Yeah, I have it.
Okay. So like in the source script for the CBC padding oracle, the idea is that we'll just define this XOR bytes function as a function to XOR 2 bytes together. It's basically like from pull import XOR bytes on 2 values. We have this padding oracle function that is going to do the padding oracle attack for us. So we are going to derive block by block from the last byte, and we'll slowly derive the entire kind of like plain text block. And this is done by, we first derive the padding byte. So originally we don't know anything, so we're looking at a padding of size of /x01. So padding byte here is going to be 1, and then our padding that we're looking for is going to be bytes of 1 times 1, so it will be b/x01. So that's what padding is going to be given. At the same time, now that we know this padding, we are going to modify our IV or the previous ciphertext block by XORing our known data. Wait. Oh no, this comes in later. For now, you will notice that this is going to just be the padding because known data is empty. There'll be a reason why we are doing this, but it comes later. So right now, known data is empty. Padding is going to be the padding byte, so input IV will be the padding byte for now. So it will be just /x01. Then we are going to essentially, so like input IV will be nothing first, and we're going to guess an I, which is going to be our x value, whereby x is going to be used to XOR, and we hopefully will get one that measures our padding. So we then structure our guess IV, or our guess like ciphertext block, to be 0 times 16 minus guess IV plus guess IV. So this is just our way of trying to show that we are doing, how do I put this? Because we are just guessing in x whereby it only modifies the last byte, we need 15 previous bytes of null bytes to kind of like pad out the prefix, so it's exactly 16 bytes long. We then send this packet followed by a ciphertext block, and we use guess IV as our IV, and the ciphertext block is our ciphertext. Let's scroll up. So this where our IV is now our x, and our ciphertext is now our C1 in this picture here. Then we send the packet over. So for reference, this challenge uses JSON object encoding as a way to encode data. So we have to do some like conversions accordingly. But once we send the data over, we will receive the result, and then we check if the error is inside the line that we receive. So if the error is not inside, that means there's no padding error, which means that whatever it was decrypted to /x01. So recall we got that P1 XOR C0 XOR X must be the padding byte. So we can do P1 XOR C0 is padding byte XOR I. Scroll down. And from there, we are able to derive that the known data, or our recovered plain text, must be this value. While for known data, we're using P1 XOR C0. Later on, at the very end, we will XOR away this C0 by XORing it with previous IV. Yeah. So that's essentially how the attack works, but that's to recover the last byte. Scroll back up. So now we're going to show why it works for the next byte. So with pointer as 1, we've recovered the last byte of P1 XOR C0. Then that means that we're now looking for a scenario where our padding byte is going to be /x02/x02. So if we have the last byte of P1 XOR C0, we want to find an x at that last byte such that it will automatically XOR into /x02. That's what this is doing, where the known data, which is what we already know, is XORed with the expected padding output, such that it will XOR to 02. Then we do our guess IV again, so that we guess the next value, here this x, such that eventually we'll hit a /x02, and then we pad the rest with 00 to ensure it's length 16. Then we repeat this process to slowly recover P1 XOR C0. Then the last step is basically XORing it back with C0 to kind of like fix everything. Yeah. So
that's the whole attack. So we basically call padding oracle with C0 on with the flag IV as a previous block, followed by C1 with C0 as a previous block, and C2 with C1 as a previous block. And when we print those out, it should give the flag. We can run it, and hopefully it does.
It takes kind of long though.
No, it should be fine.
Yeah, like now I'm saying this from yesterday where we ran it and we had to like go on to other content while waiting for it to run.
Nah, it will take a while, but it should. I did leave debug messages inside.
Yeah.
So you can see that these are the recovered bytes of P1s or C0, and slowly but surely, when this code finishes running, it will print out the flag. You can trust me on that. Yeah. And we can go back to the slides while this is running. So for reference, if anyone is interested as to why we're covering CBC padding oracle to begin with, the reason is because actually in 2016, there was a known vulnerability in OpenSSL, which is this like, OpenSSL is this big library that is responsible for a lot of your encryptions and whatnot, and they found that actually their CBC implementation has a padding oracle. So in a sense, attacks like these, as like weird as it is with all their weird contexts and like their weird like scenarios that you're in where you're able to have this and that, it can in fact exist in the real world, and this was in 2016 if I'm not wrong. So that's kind of cool. Yeah. And with that, we more or less come to a informal like wrap up for today's cryptography workshop. I guess some questions that one might ask is that like, just because we've learned all of these attacks doesn't mean like all of the systems that we learned before are they insecure? Like is ACB or CBC insecure because of these attacks? Not really. It depends on actually it depends a lot on what one is given with the crypto system. So in the morning, we learned what makes a crypto system secure by looking at internals. But afterwards, we are actually looking externally with knowledge of ECB as a black box, how different features that one could interact with a crypto system can lead to external vulnerabilities that can compromise integrity as well as confidentiality in some cases through IP malleability and ECB oracle attacks. And that, in a sense, is kind of like cryptography in a nutshell. There's a lot of give and take in terms of not just theory, but also playing around with systems and seeing how they can be applied. Of course, I understand that all this is quite confusing. To be fair, a lot of these attacks are actually very high level and very advanced. So it's still kudos to you all for making it this far. Yeah. So we are more or less done with this workshop, but we do have some bonus content if you guys are interested. So that depends on whether or not you guys want to go for it. Yeah. Let's show the next slide. Yeah, so we do have some bonus content if you guys want. But all of those is like for your info only. There's no like practice, no like challenges, nothing. It's just kind of those interesting stuff that we have but left out. Oh wait, did it finish running?
No, we didn't. I swiped over just now. It's still going.
Oh, when is it run? I feel like it should be quite close.
The latency is quite long. 256 times is very slow.
Times 48, yeah, 48 bytes that is going through. Yeah. It's a lot of nested for loops, and to some degree, it's also very hard to also kind of understand the vulnerabilities. But yeah, congrats on making it this far, guys.
Yeah, I have ever done a CTF challenge where the server is not in. It's like very far away from Singapore. I don't know where. I think London, and 18,000 queries took me 2.5 hours. 2 seconds on local on like my own server, by the way.
Should be done by now, right?
I hope. Okay.
There. So this is essentially CBC padding oracles in action. We will send you the source script for this so that you guys can do your own referencing, and we'll send the slides at the end of today, hopefully. Yeah.